series of lectures here. So I want to talk about this representation theory of the Drinfeld doubles, mainly on the namely the doubles of the q-deformations, which has some kind of relationship with the representation theory of the complex semisimple V groups. So it's a kind of q-deformed version of such kind of things. But before starting this real representation theoretic kind of things, I want to start with how these things are related to the theory of subfactors. And so in this talk, in the first talk, I want to focus on the subfactor theory and tensor categories and how they are related. And then in the second lecture, I want to talk on the q-deformation or the Drinfeld type, Drinfeld-Jimbo quantum groups. And in the third lecture, so I will talk on the representation theory of the usual complex semisimple V groups. And in the first lecture, I will conclude my talk by classification of the all unitary representation of such Drinfeld doubles, and then I want to prove some result on the subfactors, or namely, more precisely, the symmetry of the certain subfactors. Okay, so today I will start with how the tensor categories arises as a kind of symmetries, or the Galois group, something like Galois group of a subfactor. So but before starting that, let me start with some terminology like tensor category or something. So what is tensor category? So a tensor category is a linear category, C-linear category. Meaning that this is just a category whose morphisms are vector spaces, C vector spaces. And of course, we need a kind of tensor product type operation. So the tensor product type operation is given by a certain functor. So this is bilinear functor. Together with certain natural equivalencies, like, so as you can expect, there exists tensor unit, so there exists a distinguished object inside C, which is irreducible. Irreducible meaning that the morphism or the endomorphism is one-dimensional, and we have a natural isomorphism between this and properties. So, and the sister tensor category is a tensor category whose morphism sets are kind of something like sister algebra. So yeah, I need the concrete description or the concrete definition of this, but yeah, so whose morphism set is something like sister algebra. So of course, if you take the defined object, this is not algebra. And what we are interested in is just a case the morphisms, all the morphism sets are finite dimensional. So yeah, so in this case, the morphism set is something like matrix algebra from the star structure. Okay.
So for the endomorphisms, this is correct.
Yes, endomorphism. Yeah, but then this is not correct as a definition. So yeah, so if it's closed under the direct sum or something, then just do that. Yeah, but yeah, we are interested only in the case it's closed under the direct summons, and then in this case you can just say that endomorphism set is always C algebra. Yes. Okay. Anyway, then so our main example comes from the subfactor or the Tuma factor. So when you start with a Tuma factor, one can form a huge tensor category, which is so you consider all of the bimodule over n. So finite index, extremal bimodules over n. So this is simply the Hilbert space with left-right m actions. Of course, normal. With same finite left and right Murray-von Neumann dimension. Or von Neumann dimension. Then actually this carries a natural product, natural tensor product. Which is so-called Cons-Baggio tensor product. So just as the usual kind of algebra theory, so one can form a Hilbert space, which is whose tensor product is taken over M. So this is actually the definition is a kind of bit tricky, but still one can form these kind of things. Well, but still, yeah, we are only working with finite index case, so it should be easier. Anyway. Okay. And then for this object and this tensor product, and together with a natural morphism just by invariant homomorphism between the Hilbert spaces, this forms a tensor, sister tensor category, whose object sets are always, whose morphism sets are always finite dimensional. And this is really a huge tensor category. And so how this thing is related to the subfactor. So when you start with the subfactor, or yeah, to be precise, finite index and extremal. And then if you consider L2 again, then this is inside the category bimodule of n. So one can just restrict the m action to n, then L2m is automatically an n bimodule, of course. And then, so this is not only a bimodule, so simply because this m is algebra, is a von Neumann algebra, so in particular this is an algebra, so this carries a kind of natural algebra structure. So in the sense that the product gives rise to a map from here to here. And then together with a bit of consideration, so this algebra structure also gives rise, reconstructs the product on N. So this L2M with product reconstructs N containing N. So the classification problem, the subfactor really is nothing but the classification of the algebra object inside bimodule over N up to certain isomorphism. But actually, so yeah, as you can see, the problem is not get easier. I mean, so it's just a reformulation, just in this case. I mean, just in this. Yeah. So so let me mention. So these two objects, so-called Q system by Longo. Anyways, so what we want to think about is the classification of Q systems, but it's almost kind of impossible to do that. So instead of classifying these all Q systems, one can think of the tensor category generated by Q. So instead we consider tensor category generated by Q. So this is so this is C is the full subcategory. Generated by all or with objects are equal to all direct sums of Q, the tensor product of Q. So all direct sums of direct sums of yeah, so this is usually fairly small tensor category, so reasonably small. And so one can divide the problem, one can divide the classification problem into three parts. So can you see it? Problem of a subfactor into the following. So first of all, we need to determine how this tensor category looks like. So the classification of, yeah, I should say rigid. So rigid simply means all objects have its conjugate. So in this case, we have a conjugate bimodule, and so this is closed under the conjugate bimodule. And yeah, so first of all, we need to classify all rigid sister tensor category, and then we classify all Q systems inside it. So, and the third problem is so the classification of Q in C. And the third problem is the functor, fully faithful functor from C to the bimodule category. So how this category is embedded into the category bimodules. And okay. And actually, so the first of all, the first problem is kind of impossible. So this is too hard to. I mean, this is too complicated in a sense. So this is impossible. So, yeah, I don't have space to write. The first one is impossible. So actually, this contains classification of all groups. Which I will explain later. And the second one is, so this is a kind of combinatorial problem. So it's not kind of operator algebra. I mean, so this is kind of combinatorial. And done case by case for each C, each sister tensor category. So, and should be done. So I will explain more detail later. And the third one is the most interesting question. The third one is interesting. So I will illustrate how these questions is related to the group actions. And so I want to say why this kind of thing holds. I mean, why I said it this way, and where's the, yeah. Feel free to ask any questions if anything is not clear. Okay. So when you start with a group, say discrete group, then one can always form a tensor category, which I write in this way. So this is a category of finite dimensional G-graded Hilbert spaces. So this is simply Hilbert space with a given direct sum decomposition with the index indexed by the group element. And then this carries a natural tensor product. So that grading on the tensor product is given by the product of the group elements. So this is just this. Then this is a category. I mean, this is a sister tensor category, and which is rigid actually. So this is a rigid sister tensor category. And of course, this category remembers original G. I mean, so if you just look at the irreducible object, so irreducible object is parameterized by the element of G. Just by so the irreducible object is nothing but the one-dimensional Hilbert space whose grading is concentrated in some group element. And the tensor product is nothing but the group product. So this really remembers original G. And so, of course, so if you want to classify all rigid sister tensor particle, you need to classify all G, so it's impossible to solve. The first one is, yeah, too difficult. And it's not what we aim. And okay, then the second question corresponds to, so actually the algebra object inside this category is up to Morita equivalence. So actually there is a natural equivalence we call Morita equivalent. So this corresponds to a finite subgroup in G, together with 2 cocycle, I guess, or 2 homology. Yes. Yeah. Anyway. So yeah, we need a bit of homological obstruction, but anyway. So we basically this corresponds to finite subgroup in G, and of course this can be done one by one, and this can be done for a kind of case-by-case argument, but there's no. This has to be done in case by case. Yeah. So this is not what we are interested in again. The third question is very interesting. So what's this embedding of this category into the bimodules? So if you have an embedding of this category into bimodules, then all objects are one-dimensional. So which means the right dimension and left dimensions are one. So each irreducible object. So for each Z in Z, we consider CZ inside. So this is irreducible objects. So the one-dimensional, and the grading is concentrated. Grading is concentrated on Z in Z. Then if you send this to the bimodule, and so if we have a functor, and if you send this by this functor, then this is isomorphic to L2 of n, because the dimension is 1 as right module. And as a left module, this is also same. This is also same to the L2 of n. But the relationship between the right action and left action might be twisted by a single automorphism. So this is for some automorphism. And a bit pity point is this automorphism is not unique. So this automorphism can be determined up to the unitary. And so due to this, so we need to be a bit careful for this. But so actually, so this functor corresponds to which we call cocycle actions. Of G on M up to some equivalence. So in this case, the third question, which I said this functor, the classification functor is nothing but the classification of the cocycle actions of the actions of the group on the 2-1 factor, which has been worked by many people like Okunian and Johnson.
How do you know that the dimension has to be preserved by that?
So yeah, that's a good question. Well, actually, it's simply because so in this case, I mean, reducible object has dimension 1, and every object has to be of dimension greater than 1 or something. I mean, so of course, I mean, it's not always preserved, but in this case, it's fine. Yeah. So, okay, anyway, so this is fine, and then so if I want to classify all the actions of groups, then it's impossible usually. I mean, so there are infinitely many or uncountably many non-conjugate or non-monocycle conjugate actions of groups without any assumption of group. So actually, the classification problem is possible only when G has a property so-called amenability. So this is possible. So the classification of group actions is only possible only when G is amenable. And then, of course, we want to, if we want to classify subfactors, then we need to define the corresponding property for the tensor category. And this is essentially done by Prof, I guess. And if once you can define this amenability, then there are a lot of other properties of the groups, like so what I'm interested in is the opposite extreme case, which we call property T. So I also want to define property T for tensor category, or higher property for tensor category of this kind. So how can we do that? So before starting these tensor category things, let me recall the definition of amenability or property T for a group. So when you start with a group, we call G is amenable. We say G is amenable. So there are two equivalent definitions. So basically, from GNS theorem, the unitary representation theory is nothing but a kind of certain function theory on the group, so like the positive definite functions. So one can give us a definition in terms of representations and the positive definite functions. So the representation theoretically, this is so the trivial representation is weakly contained in the regular representation. So if you don't know the weak containment, this is easy if you know the sister algebra theory. So this is nothing but we have. So the trivial representation extends to the reduced group sister algebra. So this is the representation theoretic definition. And one can translate this in terms of the positive definite functions using GNS. So this is this is same as saying we have a net of positive finitely supported positive definite functions, which converges to the constant function 1 in a weak in a pointwise topology. And this G has property T. So this is opposite extreme as an opposite extreme. So G has property T. The trivial representation is isolated in the space of irreducible representation of G. So actually, the space of irreducible representation of G carries a natural topology, so-called fair topology. So so one can consider the trivial representation is isolated or not. And this is same as saying for any net of positive definite functions which converges to one pointwise, then this automatically implies the convergence is uniform. And so why I said this is opposite extreme. Actually, so if G is amenable and has property T, then G has to be finite. So if you consider finite group, and if you just ignore the finite difference, then this has to be trivial. In a sense. Okay. So as I said, the classification of the group action is possible only when the group is amenable, and conversely, one can expect a kind of rigidity result for the property T group actions. Something like, let's say, for example, Popper's cyclic rigidity kind of thing. And if I want to introduce the same properties for tensor category, then of course the obstruction for this is, so for example, how can we define the unitary representation theory of the tensor category? Or equivalently, how can we define the positive definite function over the tensor category? So, in this talk, I will introduce the representation theory of tensor category, but the theory of the positive definite function theory can be treated as well. So this is done. So this approach is done by Neshiriev, Yamashita, and Bosch and Jones. And one can also do the positive definite function theory. Actually, this is earlier than their work. So positive definite functions. This is done by Prof. Okay, anyway, so one can consider, so I want to consider this representation theory of the tensor category. And how can we do this? So when you start with a representation, so when you start with a representation, unitary representation, of course. Then what I can do is, so of course this induces a map from here to, say, naturally here. So namely, one tensor z to one tensor I z to z. Of course. And if you collect all these morphisms, then this kind of remembers the original representation. And actually, for certain reasons, we should actually flip this in this way. So this is just to form a map from here to here. Yeah, of course. And of course, this CG is a kind of internal object inside the internal kind of thing in the tensor category. So I want to formulate the representation of the tensor category using this kind of idea. But still, the difficult point is this thing is not. So, for example, this H is not an object inside the tensor category or the in this case the integrated Hilbert space. So we need to change a bit of this definition. So what I will do is, so instead of considering this, we can consider so instead, so H is not kind of internal, or H or that this tensor product is a kind of not internal definition or internal object, internal notion in this category. So instead of considering this, we put a grading also in this Hilbert space with a compatible condition. So instead, we may consider Z-graded Hilbert space H with a representation of Z, which is compatible in this way. Then the representation of Z is nothing but this group. So we call it Drinfeld condition. So the Drinfeld space whose grading is concentrated on the trivial element. And then actually, this notion can be made for arbitrary tensor category. So if we have this grading, then this tensor product is tensor product inside the category, and then this map actually together with a flip is a morphism of in the tensor category. So everything can be made inside the tensor category. And of course, this is a kind of small thing, but one need to think of infinite dimensional Hilbert space. So what we started was just a finite dimensional ones. So we need to just modify a bit to include all infinite dimensional graded space. So when you start with a sister tensor category, then we consider the int category of C. No, this is just, formally speaking, this is just category of infinite direct sums of objects inside C. So, or yeah, if you want to count up, so infinite, possibly infinite. And yeah, of course, one needs to construct some morphism and kind of things, but they are all defined. One can define these kind of things, so we do not need to care about it. And then what we consider is so-called Drinfeld center or categorical center of this category. Which is defined in this way. So, category with objects is of this form. So the object, so Z is an object in C. So this is just an infinite direct sum of the object of C, and C is a. So actually, C has one index x, parameterized by x in C. So this is a morphism intertwining x tensor Z to Z tensor x. So just in this way. So so in this case, I had a morphism from CZ tensor H to H tensor CZ, which extends to the arbitrary object in the left-hand side. I mean, so the x tensor H to H tensor x. So I just mimicked the definition, so x tensor Z to Z tensor x for each object in the category. And so this also has to have a kind of the compatible condition where so this is natural in x. And also we need to have the group law. So the group law is nothing but this law. So yeah, so as I said, when you start with a finite dimensional G-graded Hilbert space, then the categorical center is nothing but this Dieter Drinfeld Z modules, Z spaces, Z modules, category of this Drinfeld. So this is really replacement. This is really a replacement of the representation theory. So actually, so I can almost stop here because I mean, so I introduced the representation theory of the tensor category, and yeah, so I need to say one thing. So actually, so the trivial element, I mean the tensor unit of the original tensor category sits inside this this categorical center in a trivial way, just by, both are isomorphic to x in a natural way. So by so we have a trivial element, and actually one can topologize the space of reducible representation of this. So yeah, so one can define the property T or the amenability in the completely same way as So for amenability we need regular grading, but anyway, so one can formulate that kind of thing in a completely analogous way. But I just want to mention just one thing. How this is related to the representation of the character algebra, which also can be seen as a kind of representation of the tensor category. So, what is a character algebra? So for character algebra is an algebra, is an star algebra generated by formal linear combination of the object inside the category. So so I just need to mention that this. Yeah, so this is just a formal symbol. So this is just one element. This is one base of the vector space. So this is nothing to do with the polynomial algebra with variable x. Yeah. So anyway, so this is just formal linear combination of this guy divided by the relation the direct sum is equal to the sum inside the vector space. And of course this has a natural base indexed by the irreducible objects. In this way. Then yeah, and then this is actually an algebra, is star algebra by the product is given by the tensor product. And the star structure is given by, so I didn't explain the rigidity, so it doesn't make sense to use this kind of thing. Yeah, but so in the case of bimodal, this is just conjugate. Yeah. And then, so when, again, so if you consider the category of the G-graded Hilbert spaces, then this is nothing but the group algebra for Z. So the representation theory of the group is nothing but the representation theory of the character algebra. So in general, what it happens is, so for each element in the Drinfeld center, categorical center, one can define star representation on morphism from 1 to z. So this is a morphism inside this category. So in the group case, so this is just a trivially graded part. So one can define a star representation of this character algebra on the space of the trivially graded elements, just in the. So the definition is a bit complicated, but so being a conjugate object means we have a natural morphism from 1 to x tensor x bar. And then using this, from the map from 1 to z, so this is identity tensor x and so on. And then one can use a half gradient here. X and so on. And then one can contract here because these are again conjugate objects. So yeah, so I have used so this is the definition. I'm sorry, I forgot to explain. For the X, right? Anyway, so one can one can always construct a star representation on certain. So this is Hilbert space actually. So on a certain Hilbert space of this guy. So I didn't mention how we topologize the topology on the how we topologize the this guy, but once if you only want to consider the spherical part or the trivially graded part like this, then one can just consider this representation. One can just consider as a representation of this star algebra, and then one can always topologize the Feld topology. So one can induce the Feld topology. And the spherical or trivially graded. And then one can also, if you fix one vector inside here, then this induces a certain function. This induces a certain function over here. And this can be considered as a function over the space of irreducible representations. So this is the equivalent to the definition of the pop-out bursts positive definite functions. So now one can also consider how all of the related notions like amenability or the probability. So yeah, amenability is nothing but the trivial representation is weakly contained in the regular grading. So actually, I will not talk on this from next week. So yeah, you can just forget about this. And property T, one can define property T to be the trivial representation is isolated with respect to this Feld topology. And the So from next week, our goal is to find an example of property T tensor category, which is not coming from the group. So what kind of tensor category? So of course, as in the group case, if you, there are a lot of property T groups or some at least non-amenable groups, but it's kind of hard to find one example with property T. And the same thing holds for the tensor categories. So so it hasn't been known for a certain time. Yeah, but so at this moment, so as far as I know, there are only three sources. So the first source is the one coming from group. So if the group has property T, then this has property T. And of course, one can use some kind of permanence property like this, or some kind of other variations of this, but this is essentially this something like this. And the second example is, so this is the one I want to talk. So if you start with a simply connected compact V group, simple V group with rank at least 2, then you take a parameter, then one can deform this compact V group. So to construct a kind of quantum group, and you can consider the representation category. Then this has property T. So this is done by myself first. And then for the case SU of rank and equations. I don't remember the year, but anyway, so after this, so Corey don't prove this for case of G2. And so I did it again for 2015, 16. So arbitrary, I can just do this here. So this is the second source. And the third source is the one coming from the Hecke pair, or the a group with a commensurated subgroup. So so when you start with a locally compact group, totally disconnected with property T, and compact open subgroup, then one can actually form a tensor category, which is again the rigid sister tensor category. Then this has property T. And this is done by myself and Stefan Ross. So as far as I know, so these are only examples which is known to have property T. So I want to focus on these things. And so from tomorrow, I will talk about the first definition of this category, and then I will move to how we prove this result. So it's until 3 o'clock, right? So let me stop here. Thank you for listening.
questions or comments for the speaker?
Yes.
How would you best reconstruct a group from the category given by the group, which you have here?
Oh, sorry.
Suppose you give me
Yeah.
one of these categories from a group,
Yeah.
and you say, find the group. How would you do it?
Yeah. So it's just so. So if you just look at all the irreducible objects inside the category, and then this is the underlying set of the group, and then if you consider the tensor product of these objects, then this precisely corresponds to the group multiplication.
And,
is it clear?
And a similar idea then would actually realize this character algebra
Yeah.
as a sort of subset of functions on the group.
Yeah, right.
Okay.
So in the case of groups again,
Yeah.
the star representation that you gave, how does that correspond to the regular representation? Because you defined the immutability using
Yes.
that.
So for the regular representation, it's a bit complicated. I mean, in terms of the half braiding or in terms of the element inside this Drinfeld center, we need to consider a kind of regular yet Drinfeld module. I mean, together with regularity on the grading component also. So it's a bit complicated, but so the definition will be like this. So you start with all irreducible objects inside the category, and then you just take the tensor product between these irreducible objects with conjugates, and take the direct sum of all of those. And then you get natural half braiding on it to make object inside here. And then another definition is much easier. So as I said, so one can always consider the positive definite function on this corresponding to each vectors inside these morphisms. And then one can define the trivial character, the regular character, or the kind of the one corresponding to the canonical trace on the group. So just by sending everything sends to 0 except for the trivial representation. So this is a function over this character algebra. And then one can consider how we can approximate this by finitely supported positive definite function. And this can be made as a definition of the amenability, which is a bit more easier.
Anyone else? Let's thank the speaker again.
So there's a cake or biscuits?